right? Don't forget to change variables back when you use a technique like this, right? Okay. So this is interesting, right? It looks a lot like the heat equation solution, but now it's got this extra term hanging around, okay? And so if I had to ask you sort of give me a physical interpretation now for what this additional term is doing, what would you say is happening? Let's say if D is greater than 0, what's happening to the heat in the system over time?
Like a
Being
sink.
absorbed.
Yeah.
Yeah, being absorbed. So this additional term, right, the plus du term, sort of absorbs, okay, or dampens heat from the system, right? And so it may be, you know, you have some infinite rod, right? I mean, I'll draw it like, it looks like a finite rod, but it goes on forever, right? And let's say you have some initial source here, g of x, right? In a typical heat equation, this initial distribution of heat would just spread out diffusively, right? But now it's as if I'm, you know, I'm like refrigerating this bar from below by some cooling force or something like that, or you know, something essentially is sucking the heat out of this, right? It's like I took an infinitely long metal bar and I threw it into outer space, you know, where the temperature is way down near absolute 0. So not only is the heat spreading out on the bar, it's being sucked out, right? And D is like, you know, how well the bar holds on to that heat, right? It controls the exponential decay of heat in the bar. If D is very close to 0, that process is happening slowly. So the bar is retaining the heat fairly well. If D is quite large, then that suggests that, you know, maybe you have the outer temperature is very cold, or the bar is not, you know, well insulated or something like that, doesn't retain the heat well. Okay. So all right. So from that problem, hopefully we learn a little bit by sort of breaking the heat equation a bit about what's going on in the original heat equation. And the last part of this question, I told you it was a short one, is so let's suppose that D is equal to D of T. Okay, that's a weird thing for me to write, but essentially let's suppose that U sub T, right, plus some function D of T times U is equal to K U X X now is our initial condition. Or sorry, our PD. And X lives in R and T is greater than 0, and I have the same initial condition again, okay? Find a change of variables, okay, that converts this to a heat equation for a new variable v of xt, okay? So maybe play with that for 5 minutes and see if you can figure out how to adapt what you learned in part A to find the right change of variables in this case. And if you need a hint, think about integrating factors from ordinary differential equations.
I was about to say, I just realized that this just boils down to being an integrating factor.
Yeah.
All right. Let's regroup. So anybody want to proffer their solution?
I got u equals v times e to the negative antiderivative of d.
Okay. Yeah, so v of xt times e to the negative antiderivative of d. Okay. And that makes it really confusing once we write a differential in there. All right, so that is, yeah, so that works in this case. And as I said in the hint, right, this really is just sort of leveraging the concept of integrating factors from linear first order differential equations, right? So so one way to derive this, right, is if I wanted to essentially if I wanted to write this down more generally, what I could do is I could say, well, I want to write u of xt equals some unknown function, and I think I haven't claimed the function f yet, so let's just call that f of t times v of xt, such that, right, u sub t equals d plus d of t, u is equal to just v sub t, right? So if I don't know at all what to put here, right, for my f of t, my rescaling of v of t, I can actually just derive a differential equation for that, and that's how you derive the integrating factor formula in ordinary differential equations, right? So so in this case, what you would get is f prime of t v plus f times v sub t plus d of t times f times v is equal to v sub t, right? Excuse me. So yeah, and then I think it's, yeah, so you can have an f here, that's fine, right? Right. Yeah, because that's gonna be in front of everything anyway. Okay. So what happens here is that if you cancel these terms out, just like you do when deriving the integrating factor in ordinary differential equations, you get f prime of t times v plus d of t f v is equal to 0. I can cancel the v's out now, and I get f prime of t is equal to minus d of t f, right? And then using, separation of variables, you can break this up, and the solution that you get from this is that f of t is equal to, some constant, right? Times e to the minus 0, integral from 0 up to t of d of s ds, right? So this would be separation of variables if you wanted to use that to solve it, right? And so when we do that, right, everything fits together to give us the cancellations that we want to reduce this to just the heat equation, right? So, so if I take this change of variables, right, that we've written down now, and I plug it in to my equation, u sub t plus d of t u is equal to k uxx, right? Then I get minus d of t e to the minus integral from 0 to t of d of s ds v plus e to the minus integral from 0 to t d of s ds v sub t plus d of t e to the minus integral from 0 to t d of s ds v is equal to k times e to the minus integral from 0 to t d of s ds v sub xx, right? So now these terms cancel, right? And I can divide by my prefactor now, and I end up with v sub t equals k vxx. And if we solve again, we're going to get that v of x is just equal to our convolution, right, with our initial condition. Notice that I skipped one part, right? But v of x0 now is equal to u of x0 multiplied by e to the integral from 0 up to 0 of d of s ds, right? Which means that that's just 1. So I get g of x there, okay? So I get phi convolved with g. And so at the end of the day, I get u of xt is equal to e to the minus integral from 0 up to t d of s ds, and then this general solution involving the fundamental solution. Okay. So so now what would this represent? This would be like if I have some time varying conductance or sort of loss rate of the heat within my bar. Maybe I have an infinitely long bar, and I can change how well insulated it is over time. I can change the ambient temperature, controlling how quickly heat leaks out of it or something like that. And so even this hyperbolic PDE, where I have a variable coefficient in time, I can basically turn into a heat equation with a change of variables, and then back out the general solution for this problem that way. Okay. So hopefully that hits on just reinforcing this method of using the general solution to get you solutions to a wider class of problems. As we talked about on Wednesday, you can extend this to the quarter plane with these extension methods. Coming up next week, what we're going to go through is I think maybe a little bit more on uniqueness methods. We've already discussed a little bit about energy methods for the heat equation. That was in the recorded lecture. I'm also going to talk some about Fourier transforms because that's a common handy method to use for not just solving the heat equation, but also solving the wave equation. But it's going to be particularly useful for finding another way to solve like inhomogeneous problems in this case, so that you don't always necessarily have to use something like the Duhamel's principle for heat equations. And then we'll go through what's called the maximum principle, which is a general property of heat equations on bounded domains, and also a useful method for finding uniqueness results. So questions about what we went over today, or anything else from the week?
I think in the beginning we specified that D was greater than 0. There wasn't a mathematical reason for that, right? It was just so that the solution would be absorbing as opposed to producing.
Yeah, I mean, it's fine. You could flip it, but you would no longer have boundedness of your solution, right? So what would happen is that if I draw u of xt now, right, as a function of this, right? If I had d of if I had d negative, right, everything's gonna, or sorry, if I have d positive, then everything's gonna go towards 0 over time, right? In this case, if d is less than 0, then I'm gonna have e to the minus dt. So this thing's gonna grow, right? And so this is gonna like actually build up over time, right? I mean, you're gonna have a smoother and smoother solution over time, but it's going to be just this flat solution that grows towards infinity. So yeah, you don't have boundedness in that case, but yeah.
And then if we had replaced d of t u with like d u sub x or something like that, like just any lower order, does this still work? We have u sub x, like the sink being proportional to the change in u.
Yeah, so then you have a quasi-linear equation, and you're going to have to resort to some generalization of method of characteristics, right? So if you're saying like if I had u sub t, u sub x, u, so now this is looking like an Advixit Burgers equation.
I meant replace the u with u sub x, so have d u sub x.
Oh, okay. Yeah, so sorry, now I understand. So yeah, now you have advection diffusion, and there's another change of variables that you can use in this case that will allow you to turn this into the heat equation.
Okay.
I think it's basically I think it's something like a solution of the form. Yeah, because now you have something like the transport operator here now, right?
Right.
So yeah, let's say if this is just a constant, right? Then you have the transport operator on the left, and so I think you can do something like v, if v is of the form v of x minus ctt or something like that. Then that V, I think, satisfies the heat equation. With what happens in the advection diffusion equation, and yeah, there's a problem like this in shear, is that you get propagation and diffusion. So you're gonna transport this initial bump of heat or whatever, and it's going to spread out over time.
Okay, interesting. Just as a first guess, I would have just assumed it would have still been like a sink term, but it would have just behaved slightly differently, like sinking faster where the slope is greater or whatnot. But that makes sense that it would move in time.
Yeah. Yeah, and you can look at, what operators are sort of showing up that look familiar to things that you've seen before, to give you some intuition. Yeah. Just like the operator that we have in this case is more like, just the typical exponential decay differential equation you get in ODEs. Yeah. All right. Okay, cool. So I will, I'll, as usual, I'll chunk this up and put it on the web, and I'll see you all on Monday. One more thing is that I think by Tuesday, I can't make it to my Tuesday office hour. But I'm happy to find other times to meet with people, because I know you're probably going to be working on homework that day. So how about if you want to meet with me another time on Tuesday, just email me. I'll probably be free like more